Okay, we are in chapter 4 now. So, this chapter is all about heat and temperature. And I'm going to go ahead and play the PowerPoint here so that I can write on here. And good news is this is the last physics chapter. And then we get into the chemistry stuff. So, and everybody usually likes the chemistry stuff more. So, that's exciting. All right. So the core concept of this chapter is that there is a relationship that exists between heat and temperature, and that involves the motion of particles, and we'll talk about that more. But it's also very related to energy, which we just got done with in chapter 3. So, our first overview is thermodynamics, and we really won't get into the thermodynamics very much, but the definition of thermodynamics is that it is the study of macroscopic. So if you ever see macro, it's kind of like big, right? So things that you can actually see involving heat, mechanical, other forms of energy, that's where like our refrigerators and heat pumps and things like that, are machines essentially, and how they use energy and how it produces heat and things like that. And then the application of that is those systems with energy, they have a energy input and therefore they have an energy output, kind of like that conservation of energy concept that we talked about in chapter 3. And again, these can be used in things like refrigerators, heat engines, heat pumps, things like that. We are going to look at more of the microscopic idea of heat and how it's related with energy. So, microscopically, we talk about the kinetic molecular theory. So you guys should know this word right here because we had it in chapter 3 whenever we talked about kinetic energy. So whenever we talked about it in chapter 3, we said if it was kinetic energy, then it was moving. So same thing here. And if it's molecular, then that's talking about molecules. And if it's a theory, that goes back to chapter 1, where it's like we have a lot of evidence that points towards this idea, but we can't really see it. So that's why it's a theory. If we could prove it, then it would be considered a law, but we can't really prove this because we don't have a microscope that can actually see this happening. So what it is it's a hypothesis about particulate or atoms that are coming together, they're moving around, and it's pretty kind of interesting because if you think about it, if you take your hands right now and you move them together, what starts to happen? Well, they should start to get warm, right? So we're moving those particles around, creating friction, and that's creating heat. Okay, so the theory is that those particles are starting to move together, rub together, and then that's causing there to be friction and therefore heat. Now, can we see that microscopically? No, but that's why it's a theory. Okay, our current view is that matter is comprised of microscopic particles called atoms. Okay, so we get more into atoms and molecules and things like that when we get into chemistry, but you do have to know some of the terminology. And then atoms combine to form molecules. Okay, so you take more than just one atom, and that's going to give you a bigger combination, which are called molecules. And then many macroscopic phenomena can be traced back to the interactions. So meaning that, even if you think about you or the desk that you're sitting at or the book that you're looking at, those are made of many, many, many atoms, but that can be traced back to those very microscopic particles, okay? So some more definitions. This chapter at first kind of has a lot of that. Elements I wish I had a periodic table on here. I actually think I do somewhere. I'll look for that here in another video so I can kind of show you. But elements are defined by a specific atom. So if you look at the periodic table, the first one on the periodic table would be hydrogen. If you look over, it would be helium. And you go on down, you get to lithium, and then beryllium, and then boron, and so on and so on. And those are basically saying that those are very, very specific, and they are unique, and you can't change it, okay? Compounds are made from more than one, so 2 or more atoms that are chemically bonded. So an example of this, let me give you an example of an element really quick. This would be like hydrogen, helium, lithium. So just those specific elements listed, you know, their own little box on the periodic table. And then compounds, an example of that would be like H2O. Okay, it's made up of 2 hydrogens, spell it right, 1 oxygen, so it's made up of 2 or more atoms, okay? So that is a compound. And then a molecule is the smallest unit that still has the properties of a compound. So that would be like if I had a glass of water, and it spilled, and it got all over the floor. If I took one little atom of that, it would have to be H2O. If I took one of those hydrogens off and it was just hydrogen monoxide, then is it still water? No, it has to be H2O. So that is the smallest it can be, where it's saying that if it's a glass of water, it's probably like, you know, millions of H2Os. They're all combined together to make that water. Okay, and then the shorthand is just like what I said here, like H2O, or a monatomic molecule would be like, it would be basically like if it was just lithium by itself. A diatomic molecule is like if you had 2 oxygens, it's kind of like 2 hydrogens, or so on and so on, of the same element that's just bonded to itself. Chlorine, things like that. Okay. Molecular interactions. Okay, so usually are attractive, causing materials to cling together. So some more terms here. You've got cohesion, which is this attractive force between like molecules. So, you know, when we spilled the water a minute ago, you know how water kind of sticks together in a puddle? It's because they're like molecules and they bond together through hydrogen bonds. So cohesion is a pretty attractive force between those hydrogen bonds, and they hold together pretty strong. I mean, obviously you can cut through water, but for the most part, water's pretty strong force. Adhesion is an attractive force between unlike molecules. So like, you know, when it rains or you take a shower or something, you get out and those, like, water is beaded up on your skin. That's skin and water, 2 different types of molecules, but they're still being basically like stuck to your skin for a little bit, right? So it's an adhesive kind of situation. Then there's repulsive interactions where like water beads up on wax and stuff like that. Okay, so we've got some phases of matter, and you guys know these, I bet. One of the first phases of matter is just solids. So solids are when you have a very rigid structure. So like that desk that you're sitting at, the computer that you're, watching on, whatever, it's a solid, okay? and it means that these bonds right here are really strong and they don't really have a lot of bend. Now, these molecules right here can still vibrate. That's what these little lines mean. They can still vibrate. You vibrate them enough, you can break that bond right there. But for the most part, they can take most of the vibrations and handle it, okay? And, 3D, and they are bonded in place, okay? The second type of phase of matter is liquids. These have a very definite volume, but not a definite shape. Meaning that, again, if I have a glass of water, this amount of water is how much I have, no matter what. If I spill it, if it spills over here on the table here, it's like this big puddle now. Is this still the same amount of water as this? Well, yeah. But is this the same shape as this? No. Typically, liquids are they're just going to be the shape of whatever container is holding them. So if it just spills on the table, then it just has this sort of flat shape. So their bonds are weaker. They're still cohesive. They're still attached. This puddle of water is together, but it's not as strong as the phase of solid. And then they do allow vibration and rotation, just the same, like as the solid, only more so, right? Because liquids can move around and slosh around and kind of like I said, they can change shape. Can you change shape of a solid very easily? No. Oh, and then for some reason my stuff stayed on here. So weird how random it is sometimes. Okay, so we've got our third phase of matter, which is gas. And gases have indefinite volume and indefinite shape. Now, most of the time I say most of the time, I think of gases in like gas tanks, but there are gases all around us, right? We're breathing in oxygen, we're letting off carbon dioxide. Actually, we're breathing in air, but we'll get into that later. There's a little bit, of difference there. And those are gases, of course. But you can also put gases into containers, like gas tanks and stuff. Now, so they would have that shape. But really, while they're in that container, they're like bouncing around. And then if you let them out, like if I take a Febreze bottle or something and I spray it, it's going to basically just go all over the place away from each other until it's, throughout the entire room. And then eventually it goes on through the cracks and everything. So the molecules are mostly not in contact. They kind of bounce off of each other. And they do have vibration and rotation. And they just kind of go on their own free path. Okay, I'm going to stop there. Well, actually, I'm not. I'm going to talk about plasma. I think it does talk about plasma later on, but I don't really like that it doesn't talk about it. This is sort of the fourth phase of matter. And plasma is actually kind of interesting because it's like the biggest phase of matter in the universe, but it's like the least amount on Earth. So plasma is very similar to gas. It's indefinite volume, indefinite shape, bounces around. The only thing different about plasma is that it's charged. It's basically like charged gas. You find it in like lightning, fluorescent lights. It's electrical. So it is going to be, it's the most common phase in the universe. It's found, in like our stars and things like that, but it's not as much here on Earth. So I do want to point out that plasma is actually a phase all to itself. And it does show up here in a little bit. Okay, I'm going to stop the video here and then I'll start on a new one for the next section.